Hi, welcome back to this video series on program synthesis. Today I'm going to talk about functional completeness of NAND gate as well as NOR gate. What I mean by functional completeness is actually defined in the literature as well, is that NAND gate and NOR gate are foundations for all other combinatorial logic. So given a NAND gate, we can actually construct an AND gate, OR gate, NOT gate, and so on. So how I'm going to talk about today is that I will be running the synthesizer. I will ask the synthesizer to construct a circuit for me, only using the NAND gate, for example. So let's get started. So I want the synthesizer to be able to show to you suppose I want to construct a function that will only use the NAND gate. Okay, NAND gate is the only allowed gate in our construction, and the function should essentially compute regular OR, bitwise OR of two numbers x and y, but only using bitwise negation of AND, right? That's the meaning of NAND gate. Okay, so just to recall, NAND gate means you take regular AND, bitwise AND, and then you negate it. So 0 become 1, 1 becomes 0. That's basically the idea of bitwise NAND. So this is the specification, right? We want the program F to be synthesized only using bitwise NAND as the operator, and it must be equal to the bitwise OR operator. Okay, that's all. So let's give it a try. See whether we can synthesize something very quickly. Yes, we do have it very quickly. So the synthesis program can be read as follows. We are computing the function f, right? In this case, f is supposed to be, remember, just a bitwise OR. So I can very well write it as bitwise OR, right? Of two numbers x and y is nothing but, how are we computing it? It's nothing but this magic that was synthesized. It's nothing but bitwise NAND of x and x. So we first do bitwise NAND of x and x, meaning we do like this, right? We compute bitwise NAND of this. Okay, so what it means is, formally speaking, we do AND of x and x, and then we complement it. That's the meaning of bitwise NAND. Also, we do the same with y. So we do y and y. Okay, and we take one more AND, and we just do the negation of all of these. When I say negation, bitwise complement. Okay, just not to be confused with bitwise negation, which has a different meaning in Z3. Okay, so this is basically it. This is the formula that we synthesized. Remember now, the goal is to extract a function which will compute bitwise OR of two numbers x and y, but only using the NAND gate. So we achieved the goal. So it's a NAND gate, NAND gate, NAND gate. Okay, so we can continue this. Let's go back to the program and synthesize something else using NAND gate. What if I wanted to synthesize, say, just AND gate? Okay, can I do that? Should be, yeah. Again, just using NAND, we got the AND gate synthesized, which is basically 2 times the NAND. We get back the original AND. We can do more. What if your goal is to find the XOR? Can we do that? Yes, we can also compute XOR just using NAND gate. Okay, so suppose you would like to compute, say, let's do something tricky. Bitwise NOT of x. Okay, let's do that. Yep, here you go. It's nothing but x and x, of course, and then negate it. So let's think about why is this correct. It is correct because of this following reason. So what are we trying to do? We are trying to find bitwise. We are trying to find bitwise NOT, right? That can be modeled as follows. If you have a number X in binary, we basically flip the bits, bitwise not, usually we put a tilt up, means we take X and do a bitwise AND. This is not XOR symbol, this is bitwise and then we negate it or complement it. Okay, so why would this work? This would work as follows. Let's assume X is 1. In that case, 1 and 1, of course, is 1. 1's complement is 0, so we get that. What if it is 0? When it is 0, 0 and 0 is 0, we complement it, we get 1. So as you can see, we are able to implement all of the foundational combinatorial circuits or combinatorial logic operators just using NAND. Okay, this is pretty neat. Actually, we can do more, but let me now continue with my other operator that is basically bitwise NOR operator. So I'm going to replace this by NOR, which should also work for us. Yeah, it works. It's just nothing but a regular OR and then negate it, or bits complement it. Okay, so we can continue this with let's say we wanted to be able to compute bitwise AND of X and Y, but only using bitwise NOR. Can we do that? Should be. Yeah, here it is. So the program synthesizer is a pretty neat idea. Once you know the specification, and of course you have to specify the grammar, what type of constructions you wanted to use. Then it explores the state space and try to match up with your specification. In this case, this is the specification, right? The constraint is the specification. You want the black box F to be sort of synthesized, which matches the behavior that you're expecting. The behavior here is basically what you're specifying as part of the constraint. All right, that's basically what I wanted to share to you. Thank you very much.